All right, now we're going to start solving logarithmic equations. So there's a few guidelines that we want to follow when we're solving these equations. First, we're going to try to combine the log terms using properties as needed. Then we're going to change to exponential since we already know how to solve exponentials, and then we can go ahead and solve from there. There's a few little tricks with solving log equations, and that is that if both sides equal the same log or exponent, the same log, you can drop the base or ignore the base and then solve. And we have a few examples where that happens and makes it a lot easier, okay? And then one more thing, once we have an answer like x equals, because that's what solving means, we want to go back and always check your answer because we don't want any negative or zero values in the log term. So no negative or zero in log. Go back to the original equation for that as well, okay? All right, so let's just jump right in and start working through some of these problems. And the first one is log base 4 of 5x minus 1 equals 3. So first, there's nothing that I can really combine here to make it one term. I'm going to change this to exponential first. And if we remember, the base for the log becomes the base for my exponent. This becomes my exponent, and then I set it equal to the term. That's how I get rid of the log. So 5x minus 1. And then you just solve for x. So 4 to the third power is 64. 5x minus 1. We add 1 to both sides. 65 equals 5x. So x equals 13 in this case. Now, before we say, yep, this is my answer, I have to go back and check. If I were to put in 13 in my original equation, 5 times 13 minus 1, okay. This right here, the log term cannot be negative or 0. If it is, then I can't use it. So in this case, this becomes 64, so I'm good, okay? We are good to go. This answer works. I can use it. All right. Okay. So that's it. You're done. Your answer is x equals. And again, just make sure you are checking that answer. Looking at number 2, has log base 5 on the left equals log base 5 on the right. So this is one of those examples where if both sides have the same log base, I actually can drop it, ignore it, and just set the terms equal to each other. So just ignore and set the terms equal to each other. I can do this again because there's nothing else except this log base on both sides. So you just solve for x, subtract x from both sides. 3x minus 7 equals 5. 3x equals 12. So x equals 4. And again, we want to check our answer. If I were to substitute this 4 back into my original, 4 times 4 is 16 minus 7. That's not going to give me a negative or a 0, so that's okay there. And if I put it in here, 4 plus 5 is 9, so I'm good there. So then x equals 4 is my answer. Super, super important that you go back and check that the term, that set of parentheses, when you plug it back in, is not going to give you 0 or a negative. All right, moving on to the next example. This time we do have two terms. So we have log, and we don't have a base here. But remember, when we don't have a base, there is an imaginary 10. So these are both log base 10. And I'm going to combine using the properties of logs. So I know that when two log terms are being added, that actually means they're being multiplied. So I'm going to rewrite this as one log term. by saying log, and you can write the base 10 if you want, or just remember that it's there, it's imaginary. And we're going to multiply the 2x times the x minus 5. So those are the two terms I'm combining. And then that equals 2 is still there. So again, I'm able to multiply these two together because that is a property of logs. I can multiply them together. So I'm going to distribute. That's 2x squared minus 10x. It still equals 2 over here, and this is still log base 10. From here, I'm going to change to an exponential problem. Okay, so remember your base stays the same. My base is going to be 10. This becomes my exponent, so that's the 2. And then it's going to equal this term, 2x squared minus 10x. Okay, so 10 squared is 100, and I'm going to move it over to the right. So I'm going to subtract 100 to the right side. That gives me 2x squared minus 10x minus 100. And then we're going to factor from here. So from here, it's just a factoring problem. We're going to factor out a 2 from all these terms. That gives me x squared minus 5x minus 50 in this case. And then just factor that trinomial. So when I go ahead and factor that, I get x minus 10, x plus 5. So set each factor equal to 0. X minus 10 equals 0. X plus 5 equals 0. I get x equals positive 10. X equals negative 5. And again, if I were to substitute these values into my original problem, so going back to the log up here, look right here in the terms, the log terms. If you were to put in 10, for example, 2 times 10 would be 20. 10 minus 5 is 5. So this one works. If I were to put in negative 5, 2 times negative 5 gives me a negative 10. So a negative number is not something I want. So this x minus equals negative 5 is not going to work. So that's why it's really important that you go back and check your answer. Is that x value going to give you a 0 or a negative in that log term? If it is, then you're going to want to not use it. Okay. Moving on to example 4. In example 4, I need to rearrange it first. I am able to use the properties of logs, but first I need to get all the log terms to one side. So I'm going to go ahead and add this over to the left. So that gives me log base 4 of x plus 12 plus log base 4 of x equals 3. Now these log terms, they have the same base, and so because they're being added, I can combine them to one log term. So I know that I'm going to be able to multiply these together. Log base 4 of these two being multiplied. So I'm going to go ahead and just multiply them now. That gives me x squared plus 12x. And then that equals 3 on the right. And then change to exponential from here. So this is my base 4, this is my exponent to the third power equals x squared plus 12x. Oops. Okay, so let's turn this into a quadratic and factor and go from there. So 4 to the third power is 64, so I'm going to subtract the 64 over this way. 0 equals x squared plus 12x minus 64. So now that turns into a factoring problem again. What numbers multiply to negative 64 but add up to a positive 12? That's going to be x plus 16, x minus 4. And then set each factor equal to 0. So x plus 16 equals 0. That gives me x equals negative 16. X minus 4 equals 0. That gives me x equals positive 4. And before you say that these are the answers, make sure you're going back and checking, would either of these give you a negative answer in your term? So I'm looking again at the original problem. And right here, because this is a lonely x, any negative term is going to make that term negative. So x equals negative 16 is not going to work. I still have to check 4. So 4 plus 12 over here gives me 16. That's okay. And then x is just 4. So we are done. That is the answer. In this next problem, we have some terms that we can combine both on the left and on the right. So on the left side, I have log base 5 for both of these. So I know I can rewrite that as one term by multiplying the two terms together. So if I multiply these two together, I get x squared plus 4x. On the right-hand side, I also have log base 5. And that also means I can multiply these together and make them one term. So that's log base 5 of 2x squared plus 6x. So because they have the same log base on both sides, remember this is one of those problems that you can just drop the log base as long as it's the same and just focus on the terms. So I have x squared plus 4x equals 2x squared plus 6x. I'm going to move everything to one side of the equation. So I'm going to subtract the x squared and make sure you are combining like terms. And then I'm also going to subtract the 4x over. 2x squared minus 1x squared is just 1x squared. 6x minus 4x is positive 2x. So this one we can factor, but we're just going to take out a greatest common factor, leaving me with x plus 2 inside. These are each a factor. So if I set x equal to 0, I get x equals 0. If I set x plus 2 equal to 0, I get x equals negative 2. And from there, I need to just check my answer. So can these be substituted back into my original problem? When I substitute in a 0, automatically that's going to make that first term 0, so I can't have that. Going along, if I substitute in this negative 2 even to that first term, because there's nothing else, there's not like a plus 5 that would cancel it out and make it not negative, that's actually also not going to work out. So this one comes out to be no solution because both of the answers we got either make the log term either 0 or negative. So that's not going to work out for us. Okay. Moving on to number 6, now we have some natural log problems. A natural log, remember, it's just log base e, so we follow the same log properties as before. So these have the same, essentially, base, you can think of it as that. So again, these terms can be multiplied together if I wanted to simplify this to one term. So this is really ln of x squared plus x on the left, and then the right side did not change anything. Because these are both the same log base, they're both natural logs, I can just ignore them and then focus on the terms. So I have x squared plus x equals 2. Going to move the 2 over so that this can become a quadratic and I can solve for it from there. And then it's just a factoring problem. So what two numbers multiply to negative 2 but add up to a positive 1? And so I get these two, set the factors equal to 0, and I get x equals negative 2 and positive 1. So again, go back to the original problem and check. If you were to put any of these into the original equation, negative 2, for example, would make that first term negative, so I don't want that one. And then I can go ahead and check positive 1. So that would be ln of 1, and then 1 plus 1 is 2. So this one's good to go. I can leave x equals 1 as one of my answers. Moving on to number 7. So number 7 is already one term on each side of the equation. I have a natural log of 1 on one side, natural log on the other side. So I can set these two terms equal to each other and then just ignore the natural log. So I'm going to subtract 2x from both sides. 5x minus 4 equals 11. Add the 4 over. And then divide by 5. I get x equals 3. If when I substitute in 3 up here, does that give me a negative or a 0? In this case, it does not. So that's my answer. That one was an easy one. Not much work to do. Okay. Now, the last two problems that are asking us to solve for x require us to do something a little bit different. So this technically already has some exponents involved, but I'm not able to solve using exponents because they don't have the same base. These are not both 7 to some power. And I can't think of a way to turn 15 into a base of 7. It's not like if it was 49, then I could change it to 7 to the second power. So I'm going to need to use what's called a change of base. But first, I'm going to turn this into a log. So I'm going to change to a log problem. I know that originally we wanted to just work with exponentials if possible, but it made sense. It made sense for us to solve in quadratic form. Now there's really nothing I can change here, so I'm going to see if making it a log will make my life a little bit easier. When I change this to log, I have a log base 7 of 15 equals 9x, okay? And then from there, it's still, nothing's really happening, but we do have something that's called the log change of base that helps me solve for any x value when I don't have a base that I can change it to. So again, that 15, I can't change it to a base of 7 to make it easier. So I'm going to use what's called the change of base. And the change of base essentially takes your main term, so I'm going to change that to log 15 over, and then it takes your base term, so log base 7. You literally are just going to divide those two together, okay? I still have the equals 9x on the right-hand side. So I'm going to move my work over here to the right. I'm just going to type that into my calculator. The log button 15 division log button 7, enter, and I should get a decimal, and that decimal is 1.3917, and this still equals 9x. Okay, so it's a decimal. It's not going to be an exact answer like the other ones, but that's okay. And then just solving for x like normal from here. We're going to divide both sides by 9, and I get x equals 0.155. Okay, so this time the x is not perfect, but this is the only way we can really solve this one because it's not going to be a nice exact answer. And again, this was because I wasn't able to change that 15 into a base of 7, so then I could just set the exponents equal to each other like we did when we solved with exponential equations. Okay, and then number 9, again, I have e to the 3x. I can't really change 30 to be a base of e, so what I'm going to do instead is I'm going to change both of these. I'm going to multiply or take the natural log of both sides. You can think of it this way. We talked about how this is a property. The natural log of e is going to cancel out. So that's why I would want to do something like this. If I see an e by itself, I can natural log that side so that it just cancels. And then all I'm left with on the left is 3x. And on the right, I just have ln of 30, which is going to be a number. Ln of 30, when you put it in, it's going to give you a decimal answer. I'm just going to solve for x first. So that would mean that I divide by 3. And then I'm going to enter all of this into my calculator. Natural log of 30, and then divide by 3. That should give me my answer that I'm looking for, which is 1.134. Okay, so again, always try to go back and solve for x using quadratics or just factoring out, and you'll know if you'll have to do a change of base like this because there's really nothing else you can do. You can't change the number to the same base. You can't combine using log properties. Really, this would be the only option for change of base like number 8. And then for number 9, doing the natural log on both sides, because if you know this property, this usually comes in handy, makes it easier. Just remember that whatever you do to one side of the equation, you have to do to the other side of the equation as well. I did want to mention one quick thing with this problem, number 9. So if that taking the ln of both sides thing did not make a lot of sense to you, I want to show you how it's the same thing. So I'm going to just redo it over here. It's the same thing as changing this to a log. So when you change to log, the base stays the same. So you would say log base e. This would become your new term of 30 equals, and then the exponent, right, 3x. If you can do this, then we get to the same point here. We know that log base e is natural log, okay? And then we actually end up in the same place. We end up dividing by 3 to both sides, and that's going to give me the exact same answer. So however you want to think of it, you can either natural log both sides or you can change it to a log. Eventually, you'll see that log base e appears, so then you are okay with there, okay? All right, the last two questions say to find the exact answer. So I don't want any decimal answers. We're just going to leave it as a fraction if needed. So first, we're solving for x. So we're going to need to start isolating the x value by subtracting the 22 over. And that leaves me with 23 plus 4 times 6 to the x equals 5 times 6 to the x. Now, I want to deal with all the exponents all together. So what I'm going to do is I'm going to subtract this over to the right, okay, leaving with just 23 on the right-hand side. And then here's what's happening, or on the left side, and then here's what's happening on the right. We have these two terms like this, okay? And I think the easiest way to start simplifying this is for you to factor out a common factor, which in this case would be 6 to the x. Hopefully you're okay with us doing factor out the 6 to the x, and then all I have left is 5, and then minus 4. Well, 5 minus 4 is just 1, right? So 1 times anything is just going to be that. So this turns into a 1. So on the right-hand side, I really just have 6 to the x, and on the left-hand side, I just have 23. Okay, so I'm getting closer to getting x by itself. Now I'm going to change this to a log problem. So I have log base 6 of 23 equals x. And from here, in order to find the exact answer, I'm going to use that change of base again. So change of base says that I take my main term, put that on top, log base 23, and then whatever my base is, that's going to go in the denominator, log base 6, and that's going to all equal x. This is your exact answer, no decimals. You're just going to leave it like this. All right. Last problem, same process. So if you want to pause the video now and then come back and check your answers to see if you did it right. I would go ahead and start by subtracting the 23 over. That gives me 40 plus 2 times 7 to the x equals 3 times 7 to the x. I'm going to move the exponent over to the right-hand side. So 40 is the only thing on the left, and now I have 3 times 7 to the x minus 2 times 7 to the x. Then I'm going to factor out this common term that these two terms have in common. So 7 to the x times 3 minus 2, and then 40 on the left. Again, this 3 minus 2 just becomes a 1. So really I just have 7 to the x equals 40. So change this to a log. That becomes log base 7 of 40 equals x. And the only way I can get an exact answer is if I use change of base for this one. So that's log of 40 over log of 7 equals x. And that's my exact answer. So this is the end of our notes.